Wow.
Okay. Bring back some cold times.
Yes.
Miss winter.
Yeah.
What I'm going to show is the results of the data set that was collected in California in June 2010. That's where you go if you want to find snow, apparently. This data set was collected during the CARES campaign, which was aimed at completely different purposes, namely sniffing the Sacramento pollution plume as it mixed with the terpenes from the Sierra. So the flight pattern were pretty irregular, restoring Central Valley, California. But given the unprecedented amount of snow that was present on the high Sierras, we decided to insert some legs only one day that went through basically Yosemite National Park, that area. And we were lucky enough to actually nail perfectly the attitude of the aircraft, which for the research scanning polarimeter is kind of a big deal. And got up basically 15-20 seconds of data that are probably the first polarimetric data over snow, exception made for a few flights that Brian Cairns did with the RSB right in the beginning of the deployments in 1998 or 1999, I believe, ironically in the same area. But at that time, the RSB was mounted on a Cessna, and there was no information on the attitude. Therefore, those data have never been really analyzed. This is an image I took from Ralston Peak. Basically, if you look down here, there will be Lake Tahoe. This is due south. It's about 100 miles away from, 150 miles away from the area we surveyed. So this was the kind of scenery you could find just 4 days before. It was 6th of June.
I'm sorry, why wasn't the Cessna data analyzed? You say you didn't know its what?
Attitude.
Attitude.
We
So you don't have a good angular measurement.
IMU good measurements, yes.
I see, okay.
But we had aviaries. The reason why they were flying there is because Jeff Dozier and Tom Painter, Mr. Snow, they have their stations here and they were based between Colorado and California. So this area is actually intensively surveyed from all the Californian wards because of the importance of the hydrological cycle for California. So the real aim of this study, though, wasn't that much about observing snow, but trying to infer what kind of things we can do with an aerosol instrument over snow. So imagine a situation like this. This was just something I pulled from MODIS. Smoke plume over Arctic ice. Of course, we are interested in knowing if the RSP can infer some information on the grain size, for example, or the grain shape, or whatever else that deals with the surface. But we want to know if we can effectively subtract the surface when we do what we normally do, which is retrieve aerosol properties over it. And as you know, there's not really products, normal satellites data from satellite data that retrieves aerosol properties over snow, and huge areas are just thrown away because the surface is just too bright and you're trying to recover small signal, the top background of a signal that is overwhelming. So I'll go briefly through the overview of the usual things we now got used to learn about how the RSP acquires images. I have a few slides just on the transect to illustrate also the challenges due to the roughness of the terrain. And then basically go a little bit more in detail about how we analyze this data. At the end, thanks to Bastian, we also managed to infer some snow information. So we're looking at the surface. So that's perhaps the most interesting part. The rest of the yeah. RIP. So this is the RSB number 1. We recently deployed the West Coast version of it, RSB number 2. So there are actually 2 of them. This is the one that is outfitted to be integrated on the B200 NASA Langley King Air aircraft. This is a list of the campaigns that have been flown in the past dozen years or so. Yeah, it's pretty updated. We just have a deployment from last week. We'll go here. And
what is the first line of your slide mean? 470, 960, and
oh yeah, right. I skipped the for emotional reasons, the reference to the APS, but the RSB is virtually a carbon copy of, or the APS would be virtually a carbon copy of the RSB. APS being the instrument that was supposed to fly in orbit. The only difference is really that 3 channels are slightly shifted.
So whose channels are whose?
So 470, 960, 1880 belong to the RSB. And you can see they're pretty similar here, just the water band, and 443 was for ocean color. This is a Cirrus dedicated channel that was shifted a little bit towards the visible for APS. For the rest, they're pretty similar. These are scorecards or postcards that are put together from different campaigns to show the kind of sceneries we usually overfly. So you can do maritime stuff. You can do, this is the surveys we did over the Deepwater Horizon oil spill. This is the chunk of data from the Arctic deployment that Kirk published about. And this, you see, and here you see actually the day of the flight over the snow. At Sacramento, you see the rastering patterns and the detour. So this is the chunk of data that I'll be presenting here. Okay, once again, the RSB Primer. The RSB scans along the track, plus minus 60 per meter, as the aircraft proceeds. In subsequent scans, you see certain features you are interested in at different angles. As you are here, first you see a cloud over there in this scan. When you're over the cloud, you see the nadir pointing angle, and when you go further on, you see the cloud back. So what you have to do when you're back in the office is to take all different scans, go and pick the feature in different scans, and just see here, and stack it so that you actually have one column that tells you this is the feature seen from different angles. And this is the way Kirk and Brian came up a long time ago to display this kind of data. So we basically compose RGB images. We stack the subsequent scans vertically so that these are actually not maps. This is the direction of aircraft motion. There are maps only in this direction. In this direction, it will be the angle from which you see the feature. So from here, you have to do this process. Therefore, you go from the raw data to straightening the image around a certain feature. For example, here I choose the cloud altitude. This is a cloud. This black thing that is slanted as the green thing, which is the ground, is the shadow of the cloud on the ground, which is the same inclination it is on the ground. And this is RGB intensity, and this is that polarized reflectance. And this image is important for 2 reasons. One is that you can see, first of all, how looking at a cloud with your eyes or with a normal satellite, you see a white thing generally. But when you look at it with sunglasses, or like the RSB does, features like the cloud boat emerge really in stark contrast. And as you know, the spacing of these colors give you a very good indication of the cloud droplet size. Another thing that is very important is how stupid and boring the surface looks when you look at it in polarized light compared to the variations you see with naked eye. And this is very important because exploiting polarization formation, we can go and subtract the surface very effectively because it has no spectral contrast. Basically, throughout all the range of RSB measurements from 410, blue, to 2.225 micron, shortwave infrared, most of lens surfaces do not change their refractive index. So it's 1.5. 410, 470, 960. And this justifies the grayness of the surface. Therefore, you can go 2.2 micron. That wavelength, there's basically no atmospheric scattering, so you just see the surface. But that surface you see is also the surface that you will see at all the other channels, where instead you go and attempt the aerosol retrievals. So the same surface, you can subtract it from all the channels after you measure the surface of the shortwave effect. Yeah.
Does that hold true, the surface comments you made, does that hold true for water surfaces?
No, well, for the water surface, you have a variation of refractive index that goes from 134 to 128, so 2.2 micron. But also, the techniques we exploit are slightly different. I mean, the ocean becomes black, and it's all another story. So that's why we have a person like Jansen that does that part.
Well, I was asking not necessarily because we're interested in inundation, right? So my question is that also the case for flooded surfaces?
Oh, if you have flooded surfaces.
On land?
I don't know. It depends on how much water is there. But one thing that I know is that there's a paper on exploiting sampling to study flooded areas. So that's a water feature that you can exploit there.
You said it's gray, but the top of that polarized reflector is bright.
Here?
Yeah.
This is, well, I don't know how much bright, but there's always some haze at the most extreme
Michael,
angles.
can you turn the light off?
Do you see that brighter here? So you see
Yeah, that brightness. Yeah, that's not
Okay.
great. That's
Just leave it.
That's an effect. Huh? Multiple scattering from haze and but you see it doesn't vary in these directions.
yeah.
See what I mean?
I thought spectrally was up and down.
It is no.
Oh, up and down is the angle. I'm sorry.
Yeah, right.
Right.
So
I forgot.
it
Okay.
depends on the viewing geometry. But
Yeah.
see,
No,
we
up
should
and
see
down is the
this.
angle. Got it. Never mind.
Okay. So the B200, when we overflew the transect, has had a downward-looking camera, so you can basically stitch together the images, and this shows the area we surveyed. In the analysis, I choose 3 scenes. One is a glacier, one is more like a valley, and this is North Peak. Basically, this is the border of Yosemite. So this is Inyo, that's Yosemite, that's Mono Lake. And you can take this and just blanket Google Earth with it. So you get an idea of the roughness of the terrain, which was maybe the biggest of the uncertainties we had. Here you also see how much the terrain varies there. Mile High, Yosemite Valley over here. Basically, the area is back here. This is Yosemite Valley. This is Half Dome. That's the living legend of El Capitan. So after AGU, I also went up Mount Dana. She's the second highest peak in Yosemite after Lyle Peak, this one. And basically I faced the transect right there, so this is what we did. December 11th. There's no snow, and you've seen how much snow there was on 10th of June. It was pretty. That's Connesh Mountain. Lots of papers were written here. The slopey North Peak, one of my 3 scenes. The other one is here, and the other one is here. Okay, a little bit more about how the surface is modeled. So for the total reflectance,
Yes.
Yes.
Yeah.
for the total, still awake.
Still awake.
Okay. For the total reflectance, usually there is a sum of 3 terms. This is what most satellites do. One isotropic, then there are 2 weighted terms, volumetric term and a geometric term. These account for different mechanisms of scattering. Like one is from big objects that cast shadows, the other one is more remote scattering in canopies, trees. For the polarized reflectance, instead there's only one term, which is a Fresnel term. This goes back to what we were discussing before about the features of polarized reflectors or surface. Basically, although it's not maybe intuitive, but even lens surfaces basically scatter as a collection of randomly oriented mirrors. So how you describe the polarized reflection with a Fresnel, a convolution of a Fresnel formula for reflection over a collection of random facets. And this term is rescaled with a term that basically accounts for minimal variations in the refractive index. Because if you look at the formula of this parameterization, of course it depends on the viewing geometry, as we were shown before, and almost linearly on the refractive index. That is supposed to stay constant. So this term effectively just accounts for minimal variations. Because these are similar images to those I showed before, but relative to this translate. So this is the snow we surveyed, about 20-30 seconds maybe from here to there. This is the turn of a monolith where the instruments points of all different pieces of real estate as it turns. This is the straighten up image at ground level. By the way, this is very high altitude, 3,700 meters. So there's a reason why they call it high Sierras. Again, if you look at it in polarized light, you see the kind of information content that we have. Here, you really didn't see those 2 clouds, but they emerge really well with the cloud ball. It's too little. And this is something I tried with a Modis-like combination in case you still doubted that we were looking at snow. The right thing pops up. To justify even more, or quantitatively, the claim that the surface polarized reflectance looks the same at all wavelengths, or 3 wavelengths. You can see here 2 different cases for pasture or rocks. The shape of this ball changes according to the viewing geometry, but otherwise spectrally you have no contrast. This is, you see here the residuals compared to 2250. So how different the other wavelengths are from 2250 is almost at the level of the noise of the RSB, 10 to the minus 4.
What's 470 doing?
What's
there?
470?
Well, the lavender with the
Yeah.
yeah.
At the edges of the field of view, there's always problem with, if you're crabbing a little bit, yawing with the aircraft, and you can lose, no? Multiple scattering. So you see.
Yeah, it's the same thing.
Yeah,
Because
we don't.
There's more Rayleigh interactions, more molecular
Yeah,
interactions as you go to a shorter
that's
wavelengths.
really well.
So these particular images here just observations from the RSP, so they haven't been. The atmosphere has not been completely removed from the signal. It's been mostly removed, but if there's multiple interactions between the surface and the atmosphere, those are still in there, and so there's more likely to be multiple interactions from the shorter wavelengths.
Is this from a light?
I believe so. Yeah, it's
So,
from
did you compile these figures?
Brian made those figures back.
That's the reason maybe then why you left out 410.
Yeah.
Then yeah, if you couldn't pull the data anymore when I asked you this figure. Okay.
So, but if you were to remove, if there's no atmosphere above it at all, it wouldn't look like that.
So these data were analyzed in two ways. One is the standard atmospheric correction, which is what you just mentioned. So once you have the data, you measure. If you want to look at the surface, you first have to find a way to remove the atmosphere. And this is done by simulating the atmosphere best of your capabilities with what you know from ancillary data. We also had mounted on this aircraft the Langley LiDAR. So we have a vertical characterization of the surface, of the atmosphere. Recently we have implemented in our radiative transfer code another capability which exploits the Jacobians. So basically, if you write in matrix form the reflectance as the weighted sum of your kernels, you know, if everything was pretty and linear, it would be easy to do at least a square fit. But when you have nonlinear problems, you cannot do this. And nonlinear problems here are seen in the fact that the surface and the atmosphere are coupled by multiple interactions. So it's not just A plus B equals C. But you can still do the best fit, a nonlinear least square fit, if you just basically take a derivative of the whole problem. So instead of acting on these quantities, you act on the Jacobian matrix, which is the derivative of your model there. These express the kernel weighted sums that we looked at before. And if instead of your unknown, you have the increment as an unknown. Okay, it's a little bit of technical details, but it works. This is a simulated scene where basically the signal of the surface that I was trying to retrieve is the black one, and the dashed lines are the results of the iteration, because this being nonlinear is an iterative procedure. And from the hypothetical signal is the blue one measured from altitude from the RSB. You can basically converge with very few iterations to the right answer, and that would be the red dotted line overlapping the black line. Of course, this is a simulation. I have a black line because I know what the surface is in a synthetic scene. But this black line normally wouldn't be. So the whole point would be to go from the blue to the dash red here. This is the same for the polarized reflectance, and that too converges very quickly. So we contrast these two methods, like ad hoc atmospheric correction with the results of applying the iterative scheme. So you have the first scene, the glacier up high there, the valley, and the slopey peak. The polarized and total reflectance. First of all, here you see that the total reflectance among the three scenes exhibits very, very different variations. Like it's much brighter here than it is here. Some wavelengths also show some inversions. Here we might have also presence of the red algae that are very common in the area. If you look at here, for example, the surface looks pinkish. And the albedo is generally very high. I mean, it's 12.6 or so, and almost coming to 1. Actually, not albedo, these are still reflectance. They can be converted. When you look instead at the polarized reflectance signals, the signal is very small, as we were expecting. and there's not much variations. You can see, for example, comparing this variability with the variability that you have here, there's not much. And there's some differences here, but this is a slope that is oriented 40, 45 degrees. So maybe a correction could be applied to go from apparent reflectances to real reflectances, because you should modify the solar zenith angle. They can be quite, I tried, they can be quite significant corrections, but they cannot be explaining alone what we see.
So sorry, the bottom ones are corrected for the solar zenith angle?
No, I didn't, because it would be, given the 3D effect that I have, and given the difficulty of estimating also slopes or really how we are oriented, I prefer to leave them like this to show, say, the differences you start from. So you can correct this. You can. I try with this bunch of lines that could go down 20%, 0.8. If you just put the solar zenith angle like 20 degrees away, because the slope is at 40. So you could kind of level this, but you wouldn't bring them on the same level just to this. So there's definitely differences in a bit on the surfaces, as you can see with the naked eye. This was much.
Well, no, I don't think I can see them. From those plots, I can't see them.
No, right, but in the pictures before,
Okay, in the pictures.
you see, I mean, the glaciers were white.
Yeah.
These scenes, you can definitely see that it's also some exposed terrain. The atmospheric correction, the standard one, as I said, is based on subtraction of all different contributions until you leave only that of the surface. This is done directly in the database. These things are noisy. And these are the results of the polarized reflectance corrected. So these would be basically the polarized reflectances of the surface. Now I contrast them with the one we obtained from the iterative scheme, and I contrast them by using the difference from 2250, which is what we want to know. So basically this is the spectral, the color of the snow in polarized reflectance. The 2250 is 0 because that's the reference line. I plot out different data wavelengths. And these are the surface reflectors. So from the iterative model and from the standard atmospheric correction. So the general trends are reproduced, especially, I don't know what's really going on with the 670 and the 865. There were peculiar channels, maybe late season snow or this pinkish hue given by algae. So these two show the maximum departure, but the other channels are pretty much grouped within 2 times 10 to the minus 3, which is not exactly the small residuals we were observing over land. It's 5, say, to 10 times bigger. Nonetheless, it's all small stuff. Repeating once again. And the last thing I wanted to say about this is that in another study, which was the one we did on the oil of the deepwater horizon, we had cirrus all day there, and we were managing to infer optical properties of the cirrus that was very close to the belly of the aircraft. And we modeled that with Bastian's database, and we were coming to aspect ratio, fits, roughness parameter, this is how rough the terrain analysis is, and the optical depth. This was a subvisual cirrus. Therefore, it was very interesting to see that we can retrieve such a small optical depth. The same technique was used to attempt to model the snow as a very rough ice cloud on the surface. So we squeeze the cirrus at the surface. Use the same database and see what kind of parameters we would retrieve, which is, we don't know if it's right because we don't know if dense media snow can be treated that way from a radiative transfer point of view. At least for the total reflectance, so far it seems to work for all the studies that have been done in radiative transfer in atmosphere ice coupled systems. This is an example of the fits we found. So this is 865, which we choose because it has no absorption, so we don't have that sort of uncertainty. That's the polarized reflectance we measured, I think, on CMB, the valley, which is the flat. You can see that there's a bunch of fits for different ice models. And this is roughness parameter and aspect ratio, which are the two parameterizing quantities. So it's just a different way to look at this. This is a contour plot of the root mean squared error from all the elements in the database. And quite interestingly, this shows that all the minima, which I indicated with the red dots here, have pretty well defined or belong to a valley, which is between 0.3, 0.35 maybe, roughness, whereas there's no consensus as to what the aspect ratio should be. And here we go from 0 to 50. For the way this aspect ratio is defined, this will be going towards more and more extreme columns. To look at plates, you should go from between 0 and 1, so it's kind of a different axis. But there's no normal or same aspect ratio retreat, which on the other hand could be an advantage if you're trying to build a model. Maybe it just doesn't matter. And this brings up another series of problems, because what are we really looking at? Is a snow grain even defined in a snow cover? It's not very clear.
But doesn't your plot on the left tell you that all the models are more or less the same?
Yeah, right. And these are.
So it makes sense.
Yeah, I don't rely yet to state it as a dogma after I analyze 20 seconds in the Sierras. It would be interesting, because this is a known problem, or people are really discussing about whether or not it works. One thing that is important.
So you're saying it doesn't work?
No. I'm saying so far this is what I see. It's not conclusive for me that it's applicable to all snow surfaces. That it doesn't just matter what the grain shape is. Yeah.
Is the root mean? I noticed the red in your root mean square error is 1e minus 5. On the scale, that seems like a small number still. Does
Yeah,
that
but
mean
these are defined. You can define pretty much as you want, as long as you come up with some measure of how these lines depart from your. You know why this is so small? Because the polarized reflectance is that small.
Oh, I see. It's an absolute.
So these, if you sum all the departure of these lines, you can rescale that. It doesn't matter.
Other scenes for this, or is this just the A, the C? So this is C, B.
Yeah, I have pretty much all of them, and but this is something I see.
You see that also because of roughness?
I don't necessarily come up with the same numbers for all wavelengths. I mean, physically, if you go and retrieve something like grain size, for example, all wavelengths should give you the same result. I don't have much consistency in that yet, but that's because of the high variability of these snow conditions. I don't know.
Your two parameters are aspect ratio and roughness.
Here, yes, yeah. These things I see.
But there's a third parameter, which is grain size?
No, that's yet another thing. But if you're just talking about this is something I see.
Okay.
This valley, or with more or less constrained roughness parameter, but not unambiguously defined.
You're seeing the same sort of valley in the other two scenes,
Yeah,
but with different roughness parameters?
Maybe varies. Forgot exactly the values, but I would say you never go below 0.2, like in the region of pristine ice crystals. Okay, these actually are where the models depart the most, because in this region you will start having halos. So these are the halos actually of pristine ice crystals, which really don't fit. But there's no really.
This happens.
It's approximate on the grain of snow. So it's a tilt that you have when you do the ray tracing. Instead of hitting the surface this way, you tilt it with a standard deviation. Basically linked to that. Right? Last time?
Sorry, I didn't get it.
The roughness parameter is basically standard deviation, like
Oh,
if you
yes.
had a frozen ocean.
Yeah, so it's randomly for every interaction with a photon, the facets of the particle are changed, and this roughness parameter is sort of the maximum angle that it can change them. But
Go ahead, Bashir.
I want to say one more thing, because you say the aspect ratio is not well defined, but I think most variation of polarized reflectance is within going from aspect ratio 1 basically to 0.1. So what you say, what you fit here is it's a extreme aspect ratio, and 0.1 or let me say 10 or 50. If you do
Super
this,
high long columns.
it's long columns. So it's 10 or 50 is all extreme in my sense.
Do you get so with the different roughness parameters more a different curvature then? Because you mentioned you would have you know, halos and that sort of thing. So this is quite linear. This polarized reflectance with viewing angles. So are you really fitting the flatness and that it doesn't have curvature, or is that what that of this relationship between your polarized reflectance and your viewing angle?
It's more like a
or a slope.
Parabolic.
It's missing the curvature, right? You're missing the curvature.
Variability is averaged probably by half this species. So if you have various pristine surfaces, then we will have all these optical effects. But if you have rough surface, all these optical effects are averaged out.
But I know with the cloud stuff, it seemed like you could also get a curve, so you wouldn't have big features, but instead of being so linear, you would have some curvature. And so is what you're really seeing here that flatness of it?
No, so it's
really
both
flat.
both
It's
the
like
flatness.
Yeah, it's missing
Yeah,
the
but
curvature.
I like to see this plot and then as a function of polarized reflectance, and then at around 130. No, as a function of scattering angle. Sorry.
Yeah.
Oh, I
And,
see. This is
at-
viewing angle.
At scattering angles of
yeah,
130, you would see a feature if you have pristine particles, and that's what you mean. That's the flatness of these rough particles is what you fit, but also basically
The scattering angle is pretty linear because this is principal plane. It goes from 90 degrees this side towards 180, almost linearly this way. Here I cut it -20, so this is actually 160. This is another. Let me finish with this. So, it's another problem that is known. Actually, it's better seen in this picture. Even land models fail at backscatter. So if you look, this is the scattering angle in that way. So if you go past 160, usually you see that the models, because of the Fresnel reflectance, that the backscatter is giving you theoretically zero polarization, because the reflectivity of the two perpendicular components is the same. All models fail in replicating instead quite some structure that happens at backscatter. But this is known problem also for land surfaces. It's also the case here. You see the models always go down to zero at backscatter. That's not the case in the real data, although it's very small stuff. It's not exactly known what happens there. And the conclusion, though, is that if you take the snow surface and then I basically used it as a fake surface for 20 minutes later on in the flight, where we were over the aromatic Fresnel, and mimic what we would see, like total signal, if Fresnel were covered with the same snow that we had up in the mountains, you would see that the variability of what we see of the snow surface, sorry, with the signal that instead we measured there where there was 0.1 optical depth, very normal, it's very small, you see. So as soon as you have normal amount of aerosols, these lines ramp up, and this is pretty linear process, the single scattering approximation. So this will grow till 0.8 or so. And therefore, even though the surface is not like spectrally gray as other lens surfaces, still there's probably room for a quite accurate atmospheric correction or subtraction of the surface. Because we are, you see the lines are still pretty grouped together. The only update I have, and this is the final slides, is last week we actually got finally to deploy in the year 2. The RSP is under the right wing and superpod, which is this capsule here. We got 7 hours of flight in not ideal condition, but at least right? Yeah, this is the flight we had. 7 hours, and there was a storm over the Sierra, so we pretty much lost the snow targets there. But all these targets, the green being the aeronet stations, were basically overflown with the snow-covered surface and clear skies, I would say, for most of them. And this is from though 65,000 feet, 18 kilometers altitude, so it's perspective that brings us back a little bit more towards satellite than the data we're looking at so far, which were from 9 kilometers away. On the mountains, accounting for the elevation, those data were taken 4 kilometers above the mountain. I think I will stop here because it's really late. Go ahead.
So what do you have any dependence on grain size? You didn't show. You are seeing some grain size.
We nailed it to a representative size. I think what was it, 30 microns?
Is it like a priori value or
No, it's because you know, when you parameterize, some things are not meant to depend on other things. So you can actually nail the grain size, the roughness doesn't depend on grain size. So you can choose something.
So if you change the different grain size with your tables.
We redefined. We started. Igor, what were those tables parameterized? Starting from the effective volume. You remember?
Yeah, it was the area, but the grain size for polarized reflectance wouldn't matter so much, at least if you have no absorption. So in the absorbing channels, you could have some effect of that. So that might explain a little bit the difference between different channels, so absorption. But you can also try to retrieve the grain size from the total reflectance.
We have that extra dimension in the table if you want. But we kind of, I think we recalculated, right, according to...
Yeah, we try to have the same effective radius for all aspect ratios. As the size actually changes with aspect ratio.
Another question that is you have aspect ratios of last time mentioned speed 10 to 50. So is it realistic for snow you don't have needles usually?
No, well, you could have needles actually. That wouldn't scare me so much, but I think it's just the fact that you're not in a regime, like you don't have a far field here. You don't have, it might just not have a meaning, right? So you're looking at a slab of things.
Okay, then the question is, what would happen if you actually look for retrievals that aspect ratio around 1 rather than 6? Do you have any solution, or you go to the same?
there are some minima there too, but not being the only ones, I think I might be
That's
up.
yeah.
9, 8, 6. One
But yeah, like
I think in another wavelengths we observed, there's a bunch of minima also here. So it's difficult to say, if those are realistic or not. This is
No,
I don't think there's anything realistic.
Nobody cares. The problem could be if you, for example, you can fit your data only if you assume needles, and you cannot do it with spheres. So that is a problem. And if it's
well, you cannot use spheres, real spheres. They have rainbow features and everything.
not real features, not
but
real spheres, but rough spheres.
so,
or something.
like I said, so the polarized reflections really changes if you go from aspect ratios to 1 to 10 or so, and then it's high aspect ratio, and then they don't change anymore so much as you can see here. But aspect ratio 1 and aspect ratio 10 is very different. So I don't expect that you can fit this with an aspect ratio of 1. Yes. But that dependence on aspect ratio also changes with roughness. So if you have really rough particles, then your aspect ratio doesn't matter anymore.
Okay. So what's really rough? 0.3 is really rough.
Well, so 0.7, we cut it off at 0.7 because so with this treatment of roughness, this sort of
You don't even know if you're hitting the particles at a certain point if you deal it's weird.
so 0.7 still gives sort of
Yeah, you can see
physically
here.
representative
Yeah,
results.
it's kind of reasonable if you have so the only parameters that matters is the roughness of the condensed media.
Right.
So that's the only thing you care is how it's variable on the surface. Then you don't need aspect ratio, you don't need size of the grain, because the only thing you need is how it's like waves.
Yeah.
So just to make sure I understand correctly, what you're showing is that generally snow is, in terms of polarized reflectance, it's dark and it's gray. There's
Not as gray as the surface.
So
It was-
how is it not as gray? I saw that it was kind of higher in the red. Is that what it was?
Yeah, it's you can see it in the spread of these lines, for example. So these are residuals.
So it's higher in the red.
For this particular snow, I don't trust these two bands. There was something that is not typical of a white, fresh, dry snow color. This is late season snow.
If you look at say 410 and 1593, they're pretty close to
Yeah.
0. So it's something where even at the very short wavelengths it goes back to, because most other land surfaces that divergence increases as you get farther away from 2250. It's even larger and larger.
Yeah. No, in that sense, this is good.
No, I'm just trying to see how it's different from a regular land surface.
Well, so far, if you look at the ranges of these plots, are up to 10 times the residuals I showed for the pasture or the rest. So I need a flat surface. This is what I was looking for now, in flats. Because this is that uncertainty, some with the poor conditions of that melting snow.
So the jury's still out, is what you're saying. So the jury's still out.
Absolutely, it's nice to see that we are anyway close by. But for example, these two wavelengths, I really don't know where you pick up that behavior from. It's nothing more.
Thank you.